is the experimental design. So you see this is a 12-point question. It tends to be long, it's longer, you have more time. This is one that typically students do pretty well on, but me personally, I'm kind of worried about it this year specifically because of schools being shut down in a lot of places. There is a lot of students don't have access to the usual laboratory environment that they would. And so specifically things like designing experiments may not be taking place in their high school classes the way it usually would, which creates an extra challenge when you're trying to design an experiment and you don't have the background in doing as much of that hands-on stuff yourself. So here's an example from a past test. So a student wants to determine the coefficient of static friction between a long flat wood board and a small wood block. So describe an experiment, okay, for determining the coefficient of static friction between the wood board and the wood block. Assume equipment usually found in a school physics laboratory is available. So you can see how, okay, describe an experiment. So one of the skills that you would hopefully want to learn in your high school physics class is, okay, how do I not just perform experiments, but how do I create them myself? Because it's kind of a different mindset that you have to get into. It's like, okay, well, how do I create an experiment from scratch? Sometimes they'll ask you like a few different bullet points here. Like here they ask you, okay, first draw a diagram to describe the procedure. That's not always the case. They sometimes just say, okay, describe an experiment, describe, and they might ask you to do different parts of the experiment. So like, oh, specifically focusing on, this aspect of it for a different question. Here they specifically want a diagram. Okay, so draw a diagram of the experimental setup, okay, of the board and the block. That's just to kind of show, okay, here's your board and block setup. And then describe the overall procedure to be used. Now, a lot of students, you kind of grow up learning different ways of creating a lab report and all that. Most students are used to doing like numbered steps and stuff like that. You don't actually have to do numbered steps in your procedures for this test. It's allowed. You can do numbered steps, but it's also okay to just kind of in paragraph form or in a narrative explain what you would do or what the experimenter would do, going through step by step through this through this procedure. So okay, so you would you'd set up this wood block, and you'd put weights on top of the wood block and drag it or whatever. But you basically explain, okay, I'm going to do this and then I'm going to do this, and that can be in numbered steps or not. So then again, I want to look at the grading rubric for this, just so you can see kind of how they score these. So for A, so A was the well, this is all A, but A part point 1 was drawing the diagram. Okay, so for a diagram of an experimental setup to measure the coefficient of friction, so that is feasible in a school physics lab. Okay, so anything that you could feasibly use to measure the coefficient of friction would get you a point, even if everything else is wrong. Okay, at least if you can, like, if your diagram's like, okay, I could feasibly use that, they'll give you a point for that. Now, in a school physics lab is kind of there's kind of a big window there. Okay, so that could be anything from meter sticks and stopwatches to photo gates and motion sensors and stuff like that. And those are kind of the stuff that you might not have as much access to this year, and so you might not be familiar with how that kind of stuff works. But there's almost always a low-tech answer and a high-tech answer to every question about how you could do that. And so if you're not familiar with the high-tech answer, then just go with the low-tech answer. Even if like a meter stick and a stopwatch can usually do the same thing that a photo gate or a motion sensor could, it's not going to be as accurate, but you're not necessarily being scored on whether or not you have the most accurate experimental setup possible. Just, are you going to be able to take good data on this, and do you understand the limitations and experimental error that's going to come out of that. Okay. Another point for indicating the measurements necessary for calculating the coefficient of friction. Okay, so do you know not just what the experiment should look like, but how to take data out of that? Okay, and then 1 point for indicating equipment necessary for measuring the quantities required to calculate the coefficient of friction. So, you know, have you indicated, okay, here's where the block goes, here's where I'm placing my masses, here's where my spring scale goes, and making sure that you're showing explicitly that these are the pieces of equipment that I'm using. That's not just like a scratchy diagram with some pictures on it, and it's like, okay, is that a spring scale? Is that just a piece of string? I don't know. You know, it's clearly labeled, all that stuff, to make sure you get all of your points in those areas. All right, and then for our description, so you can see in this case, actually the diagram is worth as much as the description is, which usually, you know, you get a lot more points for your description. But anyway, 3 points for a description that is consistent with the diagram part A. So let's say there's some kind of like horrible flaw in the way that you created your experiment. Okay, there's some, basically you set it up, you're in the testing mode and you just kind of get flustered and forget about the fact that you have to actually measure the mass of the wood block or something like that. As long as you are consistent with the mistake you made above, so you're not just like changing your mind halfway through and being like, now I'm going to be measuring it on a slope, and you change your experimental design so your experimental design doesn't agree with your diagram or something like that. Then you can still get the rest of the points. So your flaw that you had up above is going to cost you 1, maybe 2 points, but it's not going to cost you for everything down the line. You just need to make sure that you are consistent and show that like you understand how to do these other things. You understand how to set up procedure. You know how to set up the procedure based on your initial diagram. Then you can still get those points later on. Okay, so you also get a point for description that is conceptually valid with the methods to find quantities that would allow calculation of a friction coefficient. So that's kind of like one of the points above. So, but this is more mentioning that you know how to do, the concepts involved more than the implementation. And then 1 point for indicating a valid method for reducing experimental error. Okay, and there's always a point for reducing experimental error. Basically, and it specifically says that point, it has to be something beyond just repeated trials. So which repeated trials is good, but it has to be something like, okay, in the case of the wood block, maybe I use multiple different masses on the wood block. Okay, so that sounds like it's doing repeated trials, but you're doing repeated trials with a different basic, like you're changing a variable, right? And so by doing that, and it could be something that could reduce error or just account for it. Like using different masses would account for some kind of, small experimental error, let's say in the wood block, the mass of the wood block, or, something like that. Or it could be some way that you're reducing it by, using a photo gate instead of a meter stick in order to try and make this data as accurate as possible. But you have to somehow address that in order to get that point. And that's always the case. And then from here, it's a 12-point question. You see I've gone through 6 points here. The other 6 points would always be for some kind of data analysis. Sometimes they do the data analysis first and then do the experimental design part after that. The analysis could be somehow manipulating equations. It could be using graphs. A lot of times fitting a graph, something like that, which I find are things that students tend to understand a little better than the experimental design itself. But basically, you're looking at, okay, building those skills, and how do we? There are lots of different skills that you need to make sure that are very well addressed. And so we'd go through and do those, because they're going to be different on every question. So not every question is going to have all of those skills involved. But by doing a variety of questions, we can see where everybody's at on those.